which is inverse of a function. We define a function f and we say this is a bijection. A function should be a bijection first from a to b, then the inverse of this function f denoted f minus 1, which is the function from b to a, which is defined f of minus 1 of y, equals to x if and only if we have a function called f of x equals to y. So the first rule that you have always to check in this case, that you got an inverse only and if and only if you have a bijection, which means I could go from an element in A to B and I return as well. There is like a dual carriageway. I could go back from an element in B to A. So I need a bijection function first. So if you look to the diagram here, we have an element f of x equal x, right? We have an element which is f of A is mapped to B. Now B is also mapped to A from the other side as an onto function, okay? So in this case, the inverse A equal f of minus 1 of B. To simplify what we are saying here, you can write it as f of A is what? Is B. That's this side of the mapping. F of A is B. This is the rule. This is what the rule says. Okay? Now what we mean by f of B? F of B from this side should be the inverse. F of B inverse is A. This is what we mean by the inverse function. Take the following example. We have the set A and the set B. Now the function f is defining the relationship between A and B. So A is mapped to y, B mapped to w, C mapped to x, D mapped to v. Now what we say now, f of D is v, f of C is x, f of B is w, f of A is y. Are you with me, guys?
They're not the same as one-to-one, though.
It is, yeah. It is. It is one-to-one and onto at the same time. It should be. So every time you are looking for a function inverse, you have to have a bijection where you have one-to-one from f from A to B, and you have as well an onto. So every element in B is covered by a relationship from an element in A. Okay? Now what is the inverse? The inverse is the reflection of the image. So what we have here, f inverse of V is what? Is D. F inverse of W is B. F inverse of X is C. F inverse of Y is A. So in the exam, whether you draw this method as a diagram and you find the inverse, or you use more mathematical relationship and tricks that I'm going to teach you later on to find the inverse of the function. So let us take an example. Let a function f be the function from a, b, c to 1, 2, and 3. Now the mapping, the function f is defined by the following rules. F of a equal 2, f of b equal 3, f of c equals to 1, and is f invertible? Is there any function I could say this is the inverse of the function f? And what is its inverse? The simplest way to do this, guys, is to draw the mapping and then you figure out the opposite, the inverse. So, in this case, I have the element A, B, and we have C, and we have the elements 1, 2, and 3. Now the function f defined by f of a is 2, f of b is 3, f of c is 1. Is this our a one-to-one correspondence?
Yes.
Is it an onto function?
Yes.
Is it a bijection?
Yes.
So as long as this is a bijection, I could define the inverse. And the inverse is basically 1 is C, 2 is A, 3 is B. So f of 1 equals to C, f of 2 is f of B, f of A, and f inverse of 3 is basically B. So this is how you define or you find the inverse in the function. Now try to do this example. We have a function called f, and it's mapping z to z, such that, now the relationship f of x equals to x plus 1. Is f invertible, and if so, what is its inverse? Now, okay, so we will continue about function inverse, and there's like 4 steps you could use to find the inverse of the function. So basically, if you have a function like this, f of x equal minus 1/3 x plus 1, how you can find the inverse of the function? How you would verify? Instead of going and selecting multi-values, you will put y equals to minus 1/3 of x plus 1. Now, moved or swap y with x's, so x will be minus 1 or third y plus 1, and then you could solve the function for y as by multiplying by 3, so 3x equal minus y plus 3, and then 3x minus 3 equal minus y, or you could do y equal minus 3x plus 3, or y will be equals to, I would write it in a different way. I would write it as 3x minus 3. And this is basically after you use the inverse notation, and you say f minus 1 of x equals to minus 3x plus 3. Another example, if we have a function from the set of real numbers to the set of real numbers such that f of x equal x to the power 2 is f invertible. Now, we have done the same function when f was a mapping between the set of z integers, all integers positive and negative, to the set of integers. Now, what about real numbers? You will find that this function is basically not invertible. And the reason for that, take for example minus 0.5 and 0.5. You will find that those values have the same image in the mapping. So because it is not 1 to 1. So if you take from A, the set A, 0.5, half, okay, and minus 0.5. Now f of 0.5, how much? 0.5 to the power 2, guys.
125.
Okay, 2.5. Okay, 5 to the power 2, 25 divided by 10, 2.5. Now, minus 0.5 to the power 2 is 2.5. So you will have 0.5 and minus 0.5 both have the same image in B. So we cannot call it a one-to-one. So this is not a bijection. So we can't have a function inverse for this function. Take, for example, minus 1 over 3 and 1 over 3, and do as well find the value of f of x. You will find as well they have the same image and co-pre-image. Now, I want to start with function composition. Before I start with this, function composition. Function composition is defined by, if we have a function called f and it's a mapping. It's a mapping between elements in the set B and the set C. And we have another function, and this function we call it G. Okay? This G is another mapping from A to B. You will see now the set B is a common factor between the two functions because this set has been included in the mapping relationship of the function f and the function g. Now the composition of the function f with g, like embedding the function g inside f, you can define it like this way, or you can define it in terms of object orientation, where you have an object embedded inside another object, inherited, encapsulated in another object. This can be denoted as f composite g, where it is a function now. Define a mapping from A to C. And it's something like similar to what you could say by if I could reach C from B, and I could reach A from B. Okay, if I could reach C from B, and I could also reach B from A, there must be a function that could takes me from A to C. And we call this function the function composition fg. So f composite g of x is equal to f of g of x. So we are putting now the function g of x inside the function f. Now, to understand this further, the first step in any function composition is not to find f of something. You have to find g first. You have to find what it means, the relationship g of x first. And then you find that relation, how it basically behaves under the function f. So you take a value, you test it under the function g first, and then the result from g of x, you take that result and you test it under the function f. Now if you look to the diagram here, we have a mapping between element A, okay, and B. And we said g of A is B, okay? Now from the other side, we have as well C, and basically g of f of C, f of B is C. Now if you want to take the inverse, or the composition, you could simply say now the function f of g of A is basically C. So you will end up in C by an image for the function f of A, which basically resembles the embedding of the function g of A inside the function f. And you can write it in mathematical notation as f g of A. Now let me give you examples so you can understand how this kind of relationship is embedded in each other. Now, think always about composition in the same manner I told you. First, take a value like 1. Find g of x. You must be given two functions, g of x and f of x, okay? Now find what g of x equal. Let's say g of 1 is 2. Now go back to the function f and see how much f of 2. Let's say it's 3. In this case, f composite g of 3 is 1. I will show you more examples so you can understand what we mean by this. Consider this case. We have now a set A, a set B, and a set C. We have a function g, and this g is a mapping between the elements of the subset or the set capital A to the set capital B. Now, g of A is y. And I don't invent this. This is what I can see from the figure. G of B is W, G of C is X, G of D is also W, And the same function, this function just gives me every map between the set A to set B, okay? Now, we have another function, and this function called f. Under the function f, there is a mapping between the elements in B to the elements of C. So, f of v is I, f of w is h, f of x is I, f of y is j. Now, based on the definition we just discussed, we can find f composition G where we start from A and end up by J. Why? Because f of G of A is Y, okay? Now what is f of Y? Is J. So f composition G is basically J. Again, now what is G of B? W. Now what is f of W? H. So G composition F for the element, which is basically the starting point, which is B, is basically H. Now take, for example, G of C. G of C is X. F of X is I. So G composition G of C is basically I. Take G of D is W. F of W is H. So G composition F of D is H. Another example. Consider the case where we have two functions, f of x equal x to the power 2. Now this is like a generic rule. And we have another function called g of x where it's basically 2x plus 1. Now we want to do f composition g. So what we do? F composition g equals to f of g of x. That's the definition. That's with the definition we just considered a few slides ago. Now g of x how much? G of x equal 2x plus 1. So put this now inside the function f. Now 2x plus 1 to the power 2 is basically the function g f of x, which is 2x to the power 2 plus 1. So you embed the function g first, and then you find f of that function, how much it's equal based on the generic rule of f. Another example. We have now another function called g, which is a function from the set a, b, c to itself, and the mapping of this function as follows. We have g of a equals to b, g of b equals to c, and g of c equals to a. Now, let f be the function from the set a, b, c to the set 1, 2, 3, such that f of a equals to 3, f of b equals to 2, and f of c equals to 1. Now, how I would solve such example? How I would solve this equation? The first thing I will do, I will write the two sets and the two mapping between them. So the first thing, my starting point is not going to be anything, rather just basically define the implementation of the two functions. So we have the first set, which is A, B, C, and another set, which is A, B, and C. Now we have a third set, and this is 1, 2, and 3. Now f is saying to me the mapping is happening like this. F of A is B, f of B is C, f of C is A. Now G define another kind of relationship. G is basically defining, we have f of A mapped to 3, f of B mapped to 2, f of C is mapped to 1. There is like something not correct here, because basically, you see where I stopped? I stopped by saying, well, I could start by function g composition f, and this is g of f of x. Now once I start, I realize that there is no mapping, there is no relationship defined under this function for when I start with g of 3, g of 2, g of 1 are not defined in the original question, so I cannot continue the solution. And this is why I say it's much better to do it this way in the exam, because you could find the trick, and you expect me to be this kind of guy who always trick you. Really, yeah. In the exam, you will find lots of those tricks in the questions. So you have to be careful and do it in the right way. Let me give you another example. Okay, now we have a function f and g, and those are functions from the set of integers to the set of integers defined by f of x equal to x plus 3 and g of x equal to 3x plus 2. Without looking to the slides, would you like to try first?
Yeah.
Try it first, and then we will verify the answer. Now use the same method I teach you. Start with saying f of g of x and put now x, the function g, inside the function.